yeah, so this was also done here in 3 simulation projects with progressively longer pieces of waveguide attached. And we can see quite nicely here in the temperature how it plays a role. So here we're very close to the liquid cooled filter. The heat can flow very nicely through the aluminum, and the temperature does not differ very much. And here I have already a bit more of a hot spot here, which makes sense because I'm explicitly cooling this part after all, but not really this part here. And this grows even progressively more. So if we look at the longer waveguide extension over here, where we now have accordingly the hot spot here, and now I could think about how do I cool the waveguides? Maybe do I have also liquid cooling? Do I have an active cooling system with maybe with a fan? So we could also easily set up a fan definition here, be it axial or centrifugal type of fan. I could get again the temperature on the undisturbed waveguide or a piece of undisturbed waveguide. I could see how it interacts here. So I have a lot of options for playing around with the model, for seeing what influences what in which way, and also just getting a general impression of where there might be danger points. I could use again this simulation as a basis, go back again to EM, for example, say, okay, I now have a much hotter structure, I have temperature dependent material, how do the losses look now, and simply get an impression for what's going on there. Yeah, so with that, I think we have already a good overview. What else can we do from looking at the thermal solver? Of course, we could run transient simulations, see how long it takes for things to heat up or conversely to cool down. Especially for the CHT solver, we also have a number of further options like compact thermal model, putting in a Delphi model or 2 resistor if we were on a PCB, using a heat pipe. I mean, this is of course a simplified heat pipe model, adding a thermoelectric cooler or something like that, monitoring certain points maybe to see how the temperature or velocity develops there, see how much mass flow is through a certain area, and so on. So we have a lot of options available there, and we have a very nice link between the electromagnetic simulation and the thermal simulation. And one other thing I wanted to point out was also a few more options that are there if we're talking about PCBs. So we've just seen linking from a Microwave Studio project. On a PCB, it's often, I mean, on the filter, it was such that we would just look at the loss which results on the in the material or on the surface of the material, or however you want to see it. In a PCB, for example, we would be often driven with regard to the temperature through the component loss, which is something we can of course simulate, and is brought into the model in a case like this, or can be brought in through the EDA import. So if we take a look at the EDA import, I have a couple of thermal options here. I can set heat sources automatically on components. I can import these losses. I can get that from a CST file, from an IR drop simulation. I can also specify a CSV file. So if I have a file where I simply have component names, power, and height, I can just import that, and automatically these heat sources will be set up for me. I can of course also import material losses on the traces of the PCB on the ground planes themselves. And I can also go to the stack up, for example, do some simplification. So for example, here, if I go to simplification off, so let's do that. Okay, and finish the import. Okay. So we can see that the okay, so some parts of the history list did not run through now, of course, but the main point is we now have a detailed PCB here, which we could use for our thermal simulation. And what we had beforehand was actually the option of all, which generates finish import. Okay. Simply one block of material, a composite material, where we can see we have an anisotropic thermal conductivity, which is based on the metal content and FR4 content in the PCB, which is also something we can influence. So if we take another look at the stack up here, I have the materials here, and I could change this. I could select a new material here if I wanted to, change the properties accordingly. This would impact again on the composite material properties. I can also do a layer-wise simplification, although that is rarely useful in my opinion, unless I combine this layer-wise option. So this just means that all layers of the PCB are averaged by themselves. And I can also combine these different options, and that's where I say it might be useful. So for example, if I were to enable area restrictions, make some selection here. Okay, and let's take a quick look. Okay, and finish the import. All right. Okay, not sure what's going on. Apparently it does not. Something with the etching. Sorry about that. I'm not sure what went wrong there. Okay, so now we can see this area that I picked is actually detailed, while the rest of it is simplified. So I could, for example, define detailed areas around certain components that I want to have a special look at, and use the simplified version elsewhere. So yeah, just to make sure that the components do not, for example, see a very high thermal conductivity from the averaging process, which might not correspond to the physical reality that we have there. All right, so sorry, this was just a little trip into a side topic of PCBs. Actually, I think if I just reset the stack up to all, so, and finish the import. So now we actually also have a fan set up here, so we can take a quick look here, and we can see we have simply a Dirichlet boundary condition where the mass flow of the fan is enforced on the structure that was selected for the fan. And there's again a number of options here. We can do a nonlinear fan curve, specify the volume flow rate, the speed, the fan speed, the temperature, or dissipated heat in the fan. So there's a lot of options available. Yeah, and I think with that, my overview is mostly concluded. We have seen that we can easily couple electromagnetic and thermal simulation here. We have seen we can do this for regular structures with Microwave Studio, with the losses being imported on the structure itself. We've also seen that, especially for PCBs, we have some special options through the EDA import. And in both cases, we can use this for a back and forth bidirectional simulation as well, if we wanted to include the temperature effects.